All right, chapter 2. Essential chemistry. So you can't talk about biology without first learning about chemistry and the chemicals that we're made of. So if you take any biological system apart and you eventually end up at the chemical level. All organisms have a delicate balance of each chemical inside of them: water, hormones, enzymes, oxygen, carbon dioxide, nitrogen, phosphorus, sulfur. If an imbalance occurs, this is when disease happens. Everything inside of us is in a very, very delicate balance. If that balance gets disrupted, depending on where it is, that's when disease and disorders happen. We learned a little bit about that last semester. Matter is anything that occupies space and has mass. That is all of us, you, sitting in your chairs, your rooms, your beds, wherever you are at. You take up space and you have mass, therefore you matter. It is found on Earth in 3 physical states: solid, liquid, and gas. It's one of the first science lessons you learn. Water is the premium example of solid, you have ice; liquid, you have water; gas, you have water vapor. And matter is composed of chemical elements. It's all the elements that you see on the periodic table. You should have all taken chemistry. So you should have all, even in biology, you should have all seen the periodic table before at some point. An element is a substance that cannot be broken down into any other substances by chemical reactions. There are 92 naturally occurring elements on Earth, and the naturally is emphasized because there are some man-made elements on the periodic table. All of the elements are listed in the periodic table by their symbols. The symbols are derived from their names, but it's not always their English names. Iron, for example, its chemical symbol on the periodic table is Fe for ferrous. Ferrous is its Latin name. Gold is Au because that is from its Latin name. There's the periodic table. It's a fancy periodic table with different pictures in it of what those elements do or what they compose. There's 25 elements that are essential to people. And 6 of those 25 make up about 96% of the weight of most of our cells. And we abbreviate that SHNOPS, C-H-N-O-P-S. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those 6 chemicals make up 96% of us in different forms, different ratios, different bonding patterns. Trace elements are required in very small amounts, but they are essential for life. An iodine deficiency potentially causes goiter, and that's a picture of a woman with a goiter, which is the big bump in the neck. Fluorine is added to dental products in drinking water, and it helps maintain healthy bones and teeth. Sodium is another trace element. Calcium is another trace element that our body needs in very small amounts, or we would not function properly. Elements can combine to form compounds. Compounds are substances that contain 2 or more elements in a fixed ratio. Common compounds include table salt, NaCl, Na is sodium, Cl is chloride. You put those two together. We get the salt we use in our houses. H2O, the obvious one, water. And C6H12O6 is glucose. It's a very simple sugar molecule. Each element consists of only one kind of atom. An atom is the smallest unit of matter that still retains the properties of that element. Atoms are composed of subatomic particles. Proton is positively charged, an electron is negatively charged, and a neutron is neutral. It does not have a charge at all. So most of this should be reviewed from chemistry or even biology. I know I teach this in my biology class if you were with me your freshman year. The structure of atoms. Most atoms have protons and neutrons packed tightly into the nucleus, or the center area. Electrons orbit the nucleus. In reality, they look like a cloud that kind of drift around the nucleus. It's the picture on the right. But when we draw it how they orbit it in a circle, and then you put the electrons like on the left. And the little green positive particles, those are the protons. The brown particles behind it, they don't have a charge, so those are the neutrons. And electrons are negative. How to read the periodic table. You have the atomic number as the top number in the square. That also tells you how many protons are in the nucleus. The bottom number is called the atomic mass or the mass number. When we talk about mass, we're talking about weight, how much the element weighs. And this tells you the approximate amount of protons and neutrons that are found in the nucleus. Isotopes are alternate mass forms of an element. They have the same number of protons and electrons, but they differ in their number of neutrons. So in the picture on the left, carbon, in its normal state, has 6 protons and 6 neutrons. But there's different forms of carbon. There's carbon 13, where you have an extra neutron, and carbon 14, when you have 2 extra neutrons. And they all make up different compounds and different forms of matter. The nucleus of a radioactive isotope decays spontaneously, and it gives off particles and energy. And scientists can measure that energy that it gives off. Radioactive isotopes have many uses in research and medicine. They can be used to determine the fate of atoms in living organisms. They're used in PET scans to diagnose heart disorders and some cancers. Scientists use radioactive isotopes a lot to try to figure out how old something is, especially if it's really, really old, if it's a fossil that's been in the ground for millions of years. There's a couple extra videos if you want to learn more about radioactive isotopes. Uncontrolled exposure to radioactive isotopes harm living organisms by damaging its DNA. The 1986 Chernobyl nuclear accident released large amounts of radioactive isotopes into the surrounding area. So much so that there are mutated animals that live there now. Naturally occurring radon gas may cause lung cancer. Of the three subatomic particles, only electrons are directly involved in the chemical activity of an atom. The neutrons and the protons stay in the nucleus and kind of, they're a little click off by themselves, and they send the electrons to go do all the work. Electrons orbit the nucleus of an atom in specific electron shells. So when you draw the protons and neutrons and then the circle around it, that's the proton or the electron shell. The farther an electron is from the nucleus, the greater its energy. And the number of electrons in the outermost shell determines the chemical properties of an atom. So these are just two examples. Hydrogen has one circle, so it only has one electron shell, and it has one electron in that shell. So it can make one more bond. That's the blank circle. Carbon has two electron shells, and in its outer shell, it only has 4, but it can hold up to 8. So carbon can bond with 4 other molecules. Chemical reactions enable atoms to give up or acquire electrons, completing their outer shells. Chemical reactions usually result in atoms staying close together and being held together by attractions called chemical bonds. And the crash course on bonds is down there. That's also what your ed puzzle is on this week. So I'm not lecturing about the different types of bonds because you guys are learning about it in your ed puzzle. Covalent bonds form when two atoms share one or more pairs of an outer shell electrons. Okay, maybe I'm lecturing on it a little, but there's more details to it that you'll learn. And I tend to like GIFs. I like when things are visual and not just pictures. I like it when the pictures move and show me how stuff is put together. An ionic bond is an attraction between oppositely charged ions, where one atom will donate an electron in order to have a complete outer electron shell. Hydrogen bonds, the electron charge in water. The electron charge in a water molecule is uneven. We call that a polar molecule. You can see on the right, the hydrogens have little pluses. They're a little bit positive, and the oxygen has a little minus. The oxygen side is a little bit negative. So the attraction between neighboring water molecules, because of this polarity, is called hydrogen bonding. Cells constantly rearrange molecules by breaking existing chemical bonds and forming new ones. Such changes in the chemical composition of matter are called chemical reactions. Like I said, you guys should have all gone through chemistry. and learned how chemical reactions work. On the left side, you have the reactants, A and B. You add C. Bonds get broken and rearranged to where A is by itself, and then B and C are bonded together. Doesn't really matter what A, B, and C are. The fact that you know how a chemical reaction works. You have reactants, products, they all have to be balanced. You have to have the same number on one side as you do on the other side. Chemical reactions have reactants are the starting materials on the left, products are the ending materials on the right. That chemical reaction is wrong because the O's are not balanced. The product should be H2O2. Because if there's 2 oxygens on the left, there has to be 2 oxygens on the right. Chemical reactions can rearrange matter, but cannot create or destroy matter. That is why you always have to have the same amount on the left as the right. Water and life. Life on Earth began in water and evolved there for 3 billion years. Modern life remains tied to water. Even your cells are composed of 70 to 95% water, depending on which cells we're talking about. The abundance of water is a major reason Earth is even habitable. Water molecules stick together as a result of hydrogen bonding, like we saw in the GIF earlier. This tendency of molecules of the same kind to stick together is called cohesion. Cohesion is vital for the transport of water from the roots to the leaves of plants because it is going against gravity. It's pulling water out of the ground and sending it upward to its leaves. So it sticks together in order to move upward. Surface tension is a measure of how difficult it is to stretch or break the surface of a liquid. Hydrogen bonds give water an unusually high surface tension. That's why you'll see a lot of insects standing on water or looking like it could stand on water. They're not heavy enough to break the surface tension to be able to sink in. Temperature moderation. Because of hydrogen bonding, water has a strong resistance to temperature change. Heat and temperature are related, but they're a little different. Heat is the amount of energy associated with the movement of atoms and molecules in a body of matter. We are a body of matter. You can measure our heat. And then temperature measures the intensity of that heat. Water can absorb and store large amounts of heat while only changing a few degrees in temperature. This is why cities that live by the water on oceans or lake tend to be a little bit cooler, because those bodies of water absorb a lot of that heat. Earth's giant water supply causes temperatures to stay within limits that permit life. Oceans, seas, lakes, rivers store a huge amount of heat from the sun, while coastal areas have milder climates than inland areas. Think of the summer weather in Oceanside versus Riverside. Oceanside's a lot cooler because it has a body of water, a huge body of water, the Pacific Ocean, to absorb a bunch of heat from the sun. Riverside doesn't have that, so it gets hot in the summer. Evaporative cooling occurs when a substance evaporates and the surface of the liquid remaining behind cools down. This is what sweat does for us. This is why we sweat. Our body wants to maintain a constant temperature. If we get too hot, our body puts water on the surface of our skin to evaporate and hopefully cool us off. That is the idea behind sweat. When water molecules get cold enough, they move apart and they form ice. A chunk of ice has fewer water molecules than an equal volume of liquid water. And ice floats because it is less dense. So on the left is ice. When water molecules get cold enough, they freeze, but when they are frozen, they spread out. On the right would be actual liquid water. The molecules aren't stuck frozen in place. They're just kind of flowing against each other and fitting wherever they can. You can see that they're more dense than the picture on the left. If ice didn't float, ponds, lakes, and even the oceans would freeze solid. Life in water could not survive if bodies of water froze solid. When you see frozen lakes, it's just the ice that's on top. You know, people are always afraid of falling in because they know right underneath that water is still liquid. It's just really, really cold. Nobody wants to fall into a freezing cold body of water. Water is the solvent of life. A solution is liquid, consisting of a homogeneous mixture of two or more substances. You have all made something in your kitchen that can be considered a solution. The dissolving agent is the solvent. The dissolved substance is the solute. Think of how you make Kool-Aid. You have the powder. You put a little bit of powder of Kool-Aid in there. You put a lot of sugar in there. And then you put water in there to be able to mix it all up and hopefully dissolve the sugar and the powder. So the dissolving agent would be the water. And then the sugar and the Kool-Aid powder would be the solutes. There can be more than one. When water is the solvent, the result is called an aqueous solution. And there's an example picture for you at the bottom. This slide will come in handy when you do your lab this week. A chemical compound that releases hydrogen ions into a solution is called an acid. A compound that accepts the hydrogen and removes them from a solution is called a base. To describe the acidity of a solution, chemists use the pH scale. So acids have more hydrogen ions, which leave the rest of the water molecule, the other O and the H, with a little bit of a negative charge. And the OH minus is called a hydroxide ion. And if a solution has more hydroxide ions, it is called a base. Alkaline is another word for base. You always hear about alkaline water. Water is supposed to be neutral. There's another picture for you. The basic solution has more hydroxide ions. A neutral solution has an even amount of both. And an acidic solution has more hydrogen ions. Acids have a pH value less than 7 on the scale. Bases have a pH value that is more than 7. So the pH scale is a scale from 0 to 14. One side you have acids, one side you have bases. And in the middle, when it's 7, or even maybe a little bit below and a little bit above 7, you have a neutral solution. Water is a neutral solution, or it should be.